Thank you very much, Professor, for chairing the session. In this session, we have contributory talks from Anjan Gautam, Sikkim Manipal Institute of Technology, Sikkim, India; Divya Devi T, National Institute of Technology, Tiruchirappalli, India; Jyoti Shetty, Manipal Institute of Technology, Mahe, Manipal, India; Krishna Chandra Panigre, National Institute of Technology, Raipur, India. I request Professor Pradeep G. Bhatt, Department of Mathematics, Manipal Institute of Technology, Mahe, Manipal, to chair this session. Over to you, sir.
Hello everyone. My Hello everyone. My name is Anjan Gautam. I am research scholar under the guidance of Dr. Biswajit Dev, Department of Mathematics, Sikkim Manipal Institute of Technology, Majda, Sikkim. So I am going to give a talk on graphs with k-regular dominating set. Before starting, I would like to show you my outline, which are as follows. So I am going to give a talk. Starting with introduction, I would like to start with the definition of graph. A graph G is a pair VG where VG is a finite non-empty set whose members are called vertices, and EG is a set of unordered pair of distinct elements of VG whose elements we call it as edges. Now for a vertex V, the open neighborhood of V is defined as it is the set of all U in V such that UV is an edge of a graph G. Similarly, the closed neighborhood of V is defined as it is the union of an open neighborhood of V union V itself. Now, a subset S of a VG is called a dominating set of graph G if every vertex in V naught S has a neighbor in S. The dominating number gamma G is the minimum cardinality of all the dominating set of graph G. Now I would like to show you the example for a dominating set. If this is a graph G with 7 vertices, here the dominating set is 2, 6. As we can see that for all the vertices outside the dominating set 2, 6, they have neighbor in D. That is 3 as a neighbor 2, 1 as a neighbor 2, 5 as neighbor 6, 4 as 6, and 7 as 6. So this is the dominating graph. This is a graph whose dominating set is 2, 6, and domination number is 2. Showing more examples on dominating set, this is a graph G with domination set D as 2, 5. Here we can see that 2 and 5, there is some relation between them, that is they are adjacent. Now when we draw an induced subgraph of a dominating set D, we are going to get an edge connecting between 2 and 5 in an induced subgraph. So we can say that its dominating set is one regular, that is they are connected to with one edge. Similarly, for the same graph, we can see we can have another domination number, that is 2, 6. Dominating set, that is 2, 6. So the induced subgraph of this dominating set is going to be 0 regular. Why? Because 2 and 6 are not adjacent in the induced subgraph, as you can see that they are distance 2 apart. So this motivates us to define a regular dominating set. So the definition of k-regular dominating set is as follows. A dominating set D of a graph G with induced subgraph D is k-regular. Now if the induced subgraph D of a graph G is k-regular, then we call that set as a k-regular dominating set. As we can see that that set is dominating as well as it is k-regular. Now we will see this example. Now this is a 3 regular dominating, say this is a graph with 3 regular dominating, say D is equal to 1, 2, 3, 4. Now we can see that as this 1, 2, 3, 4 vertex comprise of a complete graph with 4 vertices, where 2 vertex, each vertex has 2 pendant vertices. Now we can see that the minimal dominating set is going to be 1, 2, 3, 4 only. Otherwise, if there can be other dominating set also as 1, 2, 3 and 5 and 6, but that is going to increase the domination number. So the minimality will lose. So the minimum dominating number is only 1, 2, 3, 4. Now when we draw in this subgraph of this dominating set, it is going to be 3 regular. Now this seems interesting because we can see this is the only dominating set in this graph, and minimal dominating set with the domination number 4, which is 4 regular. I'm sorry, 3 regular. Now this motivates us to define a strongly k-regular dominating graph, which is defined as a graph G is said to be strongly k-regular dominating graph if each dominating set of size gamma G is k-regular. That is, for every dominating set of the size gamma G of a domination number gamma G, that is k-regular. Now we will see strongly zero regular dominating graph and results for them. Now for the path Pn with n vertices, the path Pn with n vertices, then Pn is strongly zero regular dominating graph if and only if n is congruent to 0 or 2 mod 3. So we will not prove this proposition because that's easy to prove it, but we will illustrate it with the help of example. Now we can see in this figure that it is a path P7 with dominating set 2, 5, 7. As we can easily say that 2 vertices are not sufficient to dominate this graph, as 2 has covered 1 and 3, 5 has covered 4 and 6, and 7 remains still. So we have to include one more vertex. So here we have included 7. Now with this inclusion, the dominating set is 2, 5, 7. Though the induced subgraph of this dominating set is going to be zero regular, but we can see for the same graph we can have another dominating set, that is 2, 5, 6. This is also a dominating set for the same graph. Now we can see there are 2 different dominating sets, but one is zero regular, other is not. So what does this definition of a strongly k-regular dominating graph says? That every dominating set with the domination number should have k-regular, and induced subgraph should be k-regular. But as we can see in figure 6, the dominating set 2, 5, 6 is not going to be the zero regular dominating set. So that's why for n congruent to 1 mod 3, this result Pn is not strongly zero regular dominating set. So it is strongly zero regular dominating set if and only if n is congruent to 0 or 2 mod 3. Similar result with the cycle. If let Cn be a cycle with n vertices, then Cn is a strongly zero regular dominating graph if and only if n is congruent to 0 or 2 mod 3. Here also we can see that 1, 4 and 7 is going to be the dominating set for this cycle C7. Now as we see that 1 and 7 are adjacent and 4 is not adjacent to 1 and 7. So the induced subgraph is not going to be zero regular. We can get the dominating set as 1, 4 and 6 also, which is going to be zero regular, but for this to be the strongly zero regular dominating, it should have that at this dominating set should be strongly zero regular. So here it is not strong because there exists a dominating set whose induced subgraph is not zero regular. Moving further, we will see the examples of strongly one regular dominating graphs. Before that, we will a tree containing exactly 2 non-pendant vertices is called a double star. A double star is strongly one regular dominating graph if and only if each of the non-pendant vertices has degree 3 or more. We will see the example for this also. Families of double star are strongly one regular dominating graph. Now I would like to show you some examples. Now, as the preposition says that for every non-pendant vertex, that is vertex three or more. So double star is one regular as the dominating set contains this vertex and this vertex. So this set is going, I mean this graph is going to be strongly one regular. Now if we keep increasing this type of graphs so many times, that is families of double star, then that family is also going to be one regular because the dominating set will contain the middle vertex, this. Even if we draw edge between these pendant vertices randomly, this way, then also it is going to be one regular only. It is not affecting the regularness, it is one regular of these families. So this is one example of one regular dominating graph, strongly one regular dominating graph. Moving for, sorry. Okay. Now we will show the construction of strongly k-regular dominating graph. Now given a graph, how can we construct a strongly k-regular dominating graph for a given every graph? So given a graph G, we can construct a strongly k-regular dominating graph. For that, we will first take a complete graph with k plus 1 vertices. Now put at least 2 pendant vertices to each of the vertex of k plus 1, complete graph with k plus 1 vertices. Now we will select 2 vertices u and v of the complete graph and add one more vertex to both of them. That is, those vertex u and v are going to have degree at least 3 because 2 pendant vertices are already added. Now we are adding one more to each of them for u and v. Next, what we are going to do is we are going to take an edge xy from the graph G and we are replacing x with u and y with v. That is, we are going to replace that particular edge with this constructed graph. Now we are going to take the size easy number of copies of that constructed graph, that is complete graph with pendant vertices, and repeat this step with each edge of G. That is, we are going to replace each edge with this graph. Then since this is a complete graph with k plus 1 vertices, so complete graph with k plus 1 vertices is k regular. And dominating set for this graph is going to contain all the vertices from those complete graph, which is k regular. So we will illustrate this with the help of example. Here we can see if this is, suppose this is a graph, then what we are going to do is we are going to take one complete graph. It is a complete graph with 5 vertices. Now what we are doing is we are giving at least 2 pendant vertices to each edges, that is 2, 2, here it is 4, here 3, 3. So what we are going to do is we are going to determine 2 vertex with at least 3 pendant vertices, that is u and v, excuse me, with u and v. Now what we are going to do is we are going to replace this edge with this graph, that is x will be replaced by any of these vertices, this or this. Suppose we are replacing x with this vertex and y with this vertex, then our new graph is going to be like this way. Now what we are going to do is we are going to replace each such edges with this type of graphs, each such edges with this type of graphs. So we are going to get new graph. New graph where the dominating set is going to be, as we can see, the dominating set for this particular this graph is going to be these vertices, only vertices of the complete graph, this 1 2 3 4 5. So for each edges this is going to be the dominating set. So for the other edge the same thing is going to be the dominating set. For the next edge it is going to be the same. So when we collect all the dominating set of this constructed graph from graph G, we are going to get the k regular. That is, if it is complete graph with 5 vertices, then we are going to get a dominating set with 4 regular vertices. Now moving forward, so I would like to conclude my talk with the conclusion saying that the theory of domination is fastest growing as well as an important area in graph theory. So here we have characterized some classes of graph that are strongly zero regular and one regular. We have also constructed the classes of graph which are strongly k regular dominating graph. For a given graph, we are constructing a strongly k regular dominating graph. Now, our main aim is to characterize all the graphs that are strongly k regular dominating. So thank you everyone for listening to my talk. Thank you.
Good, Anjan. Good presentation you have done. Have you any questions from the audience? Hello. Any questions?
Yes, sir. I have a question. So you have considered a double star, right?
If
In
there
the
is no
example.
questions, I will ask one.
No, no.
Yeah.
No, I have a question, sir. Yeah.
Okay.
In the example, you have considered a double star. So can you consider a star with many centers and not many centers, one center and many vertices of the same kind, which have their own pendant vertices and pendant edges?
Hello.
So yeah,
I'm not.
can you consider?
I'm not getting your problem. No.
What happens if you consider instead of a double star, you have one central vertex and several vertices adjacent to it with their own pendant vertices. So it's still a tree, but you have one vertex in the center which has degree say k, and each of the k vertices adjacent to it have their own some m pendant vertices adjacent to them.
Okay, you mean actually taking a star graph and putting one pendant edge to each of those pendant vertices.
Yes. So
okay.
You can say it's a star corona with km complement.
No, actually, that graph is not going to be strongly k regular dominating because we can see that there is a dominating state. We can take a center vertex and the vertices which are at the outermost region. But that means the added vertex which we have added new vertex. Which we add new vertices. So those state collection of those state is going to be my new dominating state for this graph, constructed graph. So and that is not strongly one regular because I have
I see. Yeah.
And in example I have shown that those classes of double star are going to be my strongly one regular dominating graph. So whereas that constructed the new graph, as you have mentioned, that is not going to be strongly one regular because I can get some dominating set which is not strong, which induced subgraph is not going to be strongly one regular.
Oh, right. Okay? Yeah, I see. Yeah, I see. Thank you. Thank you.
Thank you.
Pradeep, are you online?
Hello.
Anyway, thank you, Anjan. We'll move on to another talk.
Okay, thank you, sir.
We discuss bounds for the spectral radius of the eccentricity matrix of graphs. This is the outline of the talk. First, we discuss what is eccentricity matrix and some of its properties. Then we investigate the eccentric spectrum of some graphs. Finally, we give some short lower and upper bounds for the eccentric spectral radius. Given a graph G, we can associate a matrix related to G. Such well-studied matrices are adjacency matrix, distance matrix, Laplacian matrix, etc. These matrices have been studied and applied widely. Similar to this notion, the eccentricity matrix was introduced. Let us begin with the definition. What is eccentricity matrix? Consider a simple connected graph G on n vertices. Then the eccentricity matrix is an n by n matrix, which is denoted by E of G, whose ijth entry is defined by distance between the vertices Vi and Vj if this condition is satisfied. Otherwise, it is 0. Where that notation E of Vi denotes the eccentricity of a vertex Vi, which is maximum distance from Vi to all the vertices in a graph G. The maximum eccentricity of a vertex is known as diameter of a graph G. Let us see the simple example. Yeah, you consider this graph G. The corresponding distance matrix is given here. These red color entries denotes the eccentricity of a vertex. Then the eccentricity matrix is given here. When you look at the 1/3 entry, eccentricity of V1 is 2, eccentricity of V3 is 3, so minimum is 2, which is not equal to distance between V1 and V3. So 1/3 entry in the eccentricity matrix is 0, and you whereas look at the 1/4 entry. Eccentricity of V1 is 2, eccentricity of V4 is 3, minimum is 2, which is distance between V1 and V4, which is equal to distance between V1 and V4. So 1/4 entry is retained. Like that, we can obtain the eccentricity matrix. Yes, let us list the sum of its property. And this matrix was introduced namely as a Dmax matrix by M. Randick in 2013. Why it has the name Dmax means it has some peculiar property. It retains the maximum distance in each row and each column of the distance matrix. By that you consider the distance matrix of a before discussed example. In the first row and first column, largest entry is 2. So just retain the corresponding entry. And in the second row and second column, maximum entry is 3, which occurs at 2 4th and 4th place. You just retain that entry. In the same way, the fourth matrix was obtained. Now you set the remaining entries as 0. So the fifth matrix is indeed a eccentricity matrix of G. So the eccentricity matrix can be obtained from the distance matrix by retaining the largest distance in each row and each column of the distance matrix. Right. Whereas the adjacency matrix can also be obtained from the distance matrix by retaining the smallest non-zero distance in each row and each column, which is 1. In this point of view, eccentricity matrix and the adjacency matrix are opposite. So it has another name, anti-adjacency matrix. Yes. From the definition, it is clear that the eccentricity matrix is non-negative and real symmetric. So by Schur's theorem, all its eigenvalues are real. The set of all eigenvalues of the eccentricity matrix is known as eccentric spectrum of a graph G, and the largest eigenvalue of the eccentricity matrix is known as eccentric spectral radius of the graph G. One of the most important property for connected graphs are the distance matrix, adjacency matrix, all are irreducible. Whereas this property does not hold for the eccentricity matrix. For that, you consider the eccentricity matrix of a complete graph, which is irreducible. Whereas eccentricity matrix of a complete bipartite graph with at least one partition has more than 2 vertices. And in that case, the eccentricity matrix is reducible. So, by natural to ask the question, at least for which class of graphs the eccentricity matrix is irreducible. This question was proposed by J. Wang et al. In 2018, and the same authors proved that the eccentricity matrix of a tree is irreducible. Alright. So, and people have studied the correlation between the eccentric spectral radius and some boiling point of some chemical components, and observed that the eccentric spectral radii is a better predictor of some topological indices than the spectral radius of the adjacency matrix. Right. And Randick observed that the eccentricity matrix can be different even for structurally related molecules. So It can be used to testing the graphs for isomorphism. Recent results related to eccentricity matrix are computation of the eccentric spectrum. That is, the eccentric spectrum of some classical graphs like complete graph, complete bipartite graph, star, path, cycle, etc. These have been computed. One such result is given here. This is the eccentric spectrum of cycle. These are all the results, bounds available for the eccentric spectral radius. The bounds are given in terms of entries of the eccentricity matrix, first and second eccentric degree sequence, and Wiener index. So motivated by these results, we are adding some more bounds to the eccentric spectral radius in terms of average eccentric degree sequence. Now we can go for the computation of eccentric spectrum of some graphs. For that, we need the notion of diametrical graph. We call a graph G as diametrical graph of diameter D if given any vertex U, there exists unique vertex V such that the distance between U and V is D. Some cycle of length 4 is one such simple example. Yes. Here, the maximum distance is 2, which is for x1, it attains at x4, for x2, it attains at x3. The corresponding distance matrix is given here. In each row and each column, 2 occurs exactly once. So, this gives the existence and uniqueness. So, this is an example for diametrical graph of diameter 2. And the next result gives the eccentric spectrum of composition of a diametrical graph and some connected graph. Right. The proof is quite simple. When you compute the eccentric spectrum of eccentricity matrix of G composition H, then it will look like some tensor product of two matrices. By using some properties of the tensor product, we can deduce this result. The next theorem is obtained from the previous one by raising the question: what happens if the diameter is less than or equal to 2? In fact, this result gives the relation between the eccentric spectrum and the adjacency spectrum. Now we can go for the bounds. For studying bounds, we need the notion of pseudo-eccentric regular. The ith row sum of the vertex Vi, and the ith row sum of the eccentricity matrix is known as eccentric degree of the vertex Vi. If the eccentric degree is a constant sequence K, then we call the graph G as eccentric K regular graph. The second eccentric degree and average eccentric degrees are defined like this. If the average eccentric degree is a constant sequence, then we call the graph G as pseudo-eccentric regular graph. From the definition, it is clear that eccentric regular implies pseudo-eccentric regular, but the converse need not be true. For that, you consider this example: join of complete graph on 5 vertices and complete complement of the complete graph on 3 vertices. And the corresponding eccentricity matrix is given here. Here, the average eccentric degree is a constant sequence 4. So this is a pseudo 4 regular graph, whereas the eccentric degree of the vertex V1 is 4, eccentric degree of the vertex V6 is 2. So this is not a eccentric regular graph. Yes. Consider a graph G on n vertices. Ei bar denote the average eccentric degree of the vertex Vi. Then the upper bound for this eccentric spectral radius is maximum of this set, and lower bound is minimum of this set. The both lower and upper bounds are attained only when G is a pseudo regular graph. Right. The next corollary can be proved by observing the fact that the spectral radius always lies between the maximum and minimum of the row sums. These are all some references. Thank you.
Any questions? Any questions from the audience?
Divya, unmute yourself in case you want to answer any question.
Sure, sir.
Unmute yourself. Any questions?
Your
No, sir.
okay.
No.
Divya.
Okay, then.
Divya. Yeah, Divya
Yes,
Devi.
Pradeep.
Yes, sir.
Yeah, from the graph you have done the eccentric matrix.
Yes, sir.
Your eccentric matrix, is it gives any information about the graph?
Yes, sir. Actually, it gives some structural properties. This matrix is used to find some boiling point of some chemical component. It has some application in chemical components. It is used to
Okay,
study
about the graph I am asking.
Sir, could you please repeat it?
Can you, from your eccentric matrix, can you able to get any properties of the graph? No, okay, you can think
Sir.
it.
Sure, sir.
Okay, good.
Thank you, sir.
Good luck for you.
It's Vishwajit must be having a question. Please bring him in. Okay, if it is difficult, let us go to next talk. Pradeep, please proceed.
Yeah. Okay, okay.
I'm here. I'm here. Hello.
Yeah, the next.
Can you hear me, Divya?
Yes, sir.
Actually, I just wanted to know, is there any comparison of eccentric spectral radius and spectral, say, Laplacian spectral radius or adjacency spectral radius?
Actually,
means graphs for which this, say, Laplacian spectral radius and eccentric spectral radius matches, or say distance spectral radius and eccentric spectral radius matches?
Sir, this eccentricity
characterization?
matrix has started to study in 2018. Recently, mostly 2 or 3 papers are published, but the relation between the spectral radius of distance matrix, Laplacian matrix, and these relations till now not found, sir.
Okay. Any characterization of graphs, those having same spectral and radius and eccentric spectral radius?
No, sir.
No. Okay, thank you.
Thank you, sir.
Okay, go to next.
We can call next participant.
Hello everyone, I am Jyoti Shetty. Today I am going to talk about my work in semigraph with DIBD and PBD with lambda equal to 1. The lambda is called the index of the block designs. Since semigraph is not such a familiar structure, I would like to show how a semigraph is. So this is the semigraph I have taken. Semigraph is basically a generalization of graph with multiple vertices on edges. So this is a semigraph. So you can see I have labeled it as E1 is an edge with 5 vertices, whereas E2 and E3 are 2 edges with respectively 3 vertices, and E4 is an edge with 2 vertices. There is a definition for incidence matrix of a semigraph. In the incidence matrix of the semigraph, rows are indexed with the vertices of the semigraph and columns are indexed with the edges of the semigraph. And entry is 1 if the vertex ui and edge ej are incident and 0 otherwise. And one more thing we would like to note is the definition of edge-complete semigraph. A semigraph is edge-complete if every 2 of its edges have a vertex in common. So in the previous semigraph, you can see this edge E and edge E2 are adjacent. E1 and E4 are adjacent, whereas E1 and E4 are non-adjacent because they don't have a vertex in common. I would like to brief about combinatorial design. Combinatorial design theory concerns question about whether is it possible to arrange elements of finite set into subsets so that certain properties are satisfied. In particular, the definition says a design is a pair XA such that the following properties are satisfied. First one, X is a set of elements called points and A is a collection of non-empty subsets of X called blocks. In particular, in this work, we are talking about BIBD and PBD. So let us see what is a BIBD in a block design and a PBD in the block design. A balanced incomplete block design is termed as BIBD. Is an arrangement of n points in B blocks of k distinct points each, where k is less than n, satisfying the condition that any two distinct points occur together in exactly lambda blocks. So n points in B block such that each block contains k distinct element and any two distinct points occur together in exactly lambda blocks, where lambda is the index of the block design, and this property is called the balance property. It satisfies these two given equations, and a BIBD with parameter n, b, r, k, lambda, which we have already discussed, is called the nk lambda BIBD. And a PBD is a pairwise balanced design. It's an arrangement of n points, again, B subsets called blocks, such that any two distinct points occur together in exactly lambda blocks, and blocks of sizes from a set K. So here in BIBD, all blocks of same size K, whereas here the block size may differ, but rest of the conditions remain same. And one more thing we would like to notice, where a BIBD is called a symmetric BIBD when B equal to n, that is number of points equal to number of blocks. Some of the results from the literature about block designs. One thing is a definition of incidence matrix of block design. Here the rows are indexed with the points and columns are indexed with the blocks, and 1 when a point belongs to a block and 0 when a point doesn't belong to a block. And the theorem, this theorem is about the incidence matrix, how it is related to the parameters r and lambda in particular. So if it's a NBRK lambda BIBD, then MM transpose, that is the incidence matrix of the block design at BIBD, is equal to lambda times Gn plus R minus lambda Im, and vector M is equal to K times the other vector U. It's a vector, exists a vector. And there is one more definition, that is, suppose X is a symmetric BIBD, that means B equal to M is, then if you take intersection of any two blocks, the number of elements in that intersection is equals to lambda. Main result. Here, before we start with the results, we would like to note a simple thing, that is, a semi-graph is edge complete if and only if its line graph is complete. Edge complete, we have already taught any two edges have a vertex in common, and it is complete, edge complete, a semi-graph is edge complete if and only its line graph. Line graph of a semi-graph is defined on similar lines as in case of graphs. And we have a result, the first one, lemma, that is, if M be an incidence matrix of NK1, 1 means lambda is 1 M, BIBD, then M transpose M minus KIB is A of L of G, where A is the adjacency matrix of line graph of semi-graph G, where G is not a usual semi-graph, it's a NK1 BIBD semi-graph. Next is for a symmetric NK1 BIBD, M transpose equal to M transpose M. And we term a symmetric BIBD semi-graph if the edge set of G forms a symmetric BIBD. A symmetric NK1 BIBD corresponds to an edge complete semigraph. This is the main result. So this is from the literature. M transpose is equal to lambda. As we have said, it's a relation between the parameter R lambda with incidence matrix of the block design. In particular for BIBD semigraph, lambda equal to 1. So we get this. And this we have already discussed. This is the result we have got. It's A of L of G. And since we are talking about a symmetric BIBD, B is equals to Tm. And we have already discussed if it's a symmetric BIBD, M transpose equal to M transpose M. So when we take the difference, it's equal to 0. We substitute the thing. But for any, when B equal to N, R also equal to K. And we simplify, what we get is Jn minus In is equals to A of L of G. Jn is a matrix of all ones, and this is an identity matrix of order n. So when you subtract, you get what you see is only the diagonal elements going to be 0. That is the adjacency matrix of a complete graph. So L of G is a complete graph of order n. So when the line graph is a complete graph, what about G? We have already noted that G is an edge complete semigraph with n edges. That observation, first thing we have noted. Hence, a symmetric NK1 BIBD corresponds to an edge complete semigraph. Some of the references. Thank you.
Any questions to Jyoti Shetty? If there is no questions, thank you for nice presentation, Jyoti. Okay, proceed. Next part.
From NIT Raipur. On the 100th birth anniversary of Professor C.R. Rao, I am going to present reverse order law for tensors and its applications. To do this, I organize my presentation in this way. At first, introduction, thereafter literature and motivation, then the objective drawn from it, and thereafter the research work carried out, and then the references used in this presentation. Let's start from introduction. As we see the title of the presentation, there are two keywords, tensors and reverse order laws. Let's start from what are tensors. Tensors are the generalization of scalars, vectors, and matrices to an arbitrary number of indices. That means whenever we are writing a scalar, we are just written as numbers, that is 1, 2, 3, 4, like that. So we don't need to any indexing. And whenever we are representing a vector, then we are writing AI, like that here. The vector V is represented by AI. And while in case of a matrix, we are writing it as Aij. If we generalize this indexing, that here no indexing is there, here one indexing I is there, here two number of indices I and J are there. If we generalize this, if we extend the number of indices, then this is called a term we used to call it as a tensor. And then what is dimension of a tensor? The dimension of a tensor means if a tensor A belonging to the space F I1 cross I2 cross In, in that case we call the dimension of the tensor A is I1 cross I2 cross In, and this I1 cross I2 cross In is individual, that is I1 is called the dimension of first way, I2 is called the dimension of second way, like that In is called the dimension of nth way. Also we call the dimension of its nth mode. It's I1, I2, I3. In this way we are defined. And thereafter, what is order of a tensor? Order of a tensor means the number of indices associated with it is called order of a tensor. Suppose a tensor A is represented as A equal to A I1, I2, Im. In that case, this I1, I2, Im are m number of indices. So it is called a mth order tensor. So following this definition, a scalar becomes a zeroth order tensor, a vector becomes a first order since it is only one index is there, and a matrix becomes second order tensor. That means a second order tensor is nothing but a matrix. Here, an example of a third order tensor is given here of dimension 2 cross 2 cross 3. And next, in case of matrix, we have rows and columns. In case of a tensor, we have frontal slices, lateral slices, horizontal slices, and tube fibers. Here I am taking a 3 by 3 by 3 tensor, dimension tensor, that is third order of dimension 3 cross 3 cross 3 tensor, representing here. This blue line first face represents the frontal slice. Here it represents the this one also represents the frontal slice. This one also represents the frontal slice. Let's see an example here. If we see this third order tensor, then the 0, 1, 4, 5 represents this one, represents the frontal slice. Here I am representing here, and the 3, 1, 4, 6, 3, 1, 4, 6 is also another frontal slice, and 2, 1, 3, 15 is also another frontal slice. While if we see like in this way, 0, 4, 3, 4, 2, 3, this if we take together these three, then this is a lateral slice, like that. In this way, if you choose, this becomes a lateral slice. Also another lateral slice here is 1, minus 5, 1, 6, and 1, 15. And the horizontal slices are here 0, 1, 3, minus 3, 1, and 2, 1. This is a horizontal slice. And another horizontal slice here is 4, minus 5, 4, 6, 3, 15. Next, here tube fibers. The tube fibers are nothing but they are the singly we choose. That means if we choose 0, 4, then it becomes a tube fiber. If you choose only 0, 3, 2, then it is another tube fiber in this way. So next, after knowing what are tensors, let's come to define product on it. In case of matrix, we have number of product rules. Here also a number of product rules are there. But whenever we generalize this product rule, we need to keep in mind that if it reduces to second order tensor, then it must coincide with the rule of matrix multiplication. It must satisfy the matrix multiplication, because a second order tensor is nothing but a matrix. So here in this research work, we are using Einstein product. So let's know how Einstein product is defined. Einstein product is defined for two tensors. If a tensors A and B, between A and B, if the last n dimensions of tensor A is coincide with first n indices of tensor B, then we define A star and B. And the entries of this A star and B is defined in this way. And the dimension of the resultant tensor A star and B lies in A I1 cross I2 cross Im2, K1 cross K2 cross KL. Here the simplified notation I1 dot and so on M, it represents I1 cross I2 cross Im. Here is one example for the Einstein product. If we consider the two tensors A and B from the dimension 2 by 3 by 3 and 3 by 2 by 2 respectively, and defined like this way, then we see that the last two dimensions 3 cross 2 and here the first two dimensions 3 by 2 coincides. So we can define here star 2 product. So and after using this rule, Einstein product rule, we get the resultant tensor like this. This 4 is multiplied with 4 minus 5 is multiplied with 0, 4 is multiplied with 4. In this way, we can calculate this tensor. Next, once we define the product rule, we are now ready to define ordinary inverse of a tensor. Brazil and his collaborators in the year 2013 gave the defined ordinary inverse of a tensor and ordinary inverse of a tensor for even order square tensor. A tensor X is called inverse of the tensor A if it satisfies AX is equal to identity and X star n equal to identity tensor. And this tensor is the inverse of the tensor X is denoted by A inverse, and they used this inverse of a tensor to solve the multilinear system of equations AX is equal to B, and they find that this solution is unique and the required solution is X equal to A star inverse star n B. And also they verified that the ordinary, also one can easily verify that reverse order law for A B inverse, the inverse, if A invertible, B is invertible, then A B inverse becomes B inverse star n A inverse. After that, in the year 2017, Son and his collaborators defined Moore-Penrose inverse for even order tensors. For even order tensor A, in the field I1 to In cross J1 to J1 J cross J2 cross Jn, there exists a tensor X from J1 cross J2 cross Jn to I1 cross I2 cross In, satisfying these four conditions: Ax A equal to A, X star n A star n X equal to A X, and A star n X is Hermitian as well as X star n A is Hermitian. In this case, we call the tensor X is Moore-Penrose inverse of A, and they also verified that such tensor exists for every even order tensors and it is unique. After that, in the year 2017, Behra and Misra find that if the tensors, if we consider the tensor A and B, then A, B, Moore-Penrose inverse does not satisfy reverse order law. That is, A star n B Moore-Penrose inverse does not equal to B Moore-Penrose inverse A Moore-Penrose inverse. For this, they are considering this example. I am collecting the example from this paper by the paper Behra and Misra. One can find this example, exactly this example from example 2.4 from their paper. And the literature in the year 2019 and 20, Panigrahi Misra and Liang Zhang and Stanimir independently define Moore-Penrose inverse for arbitrary order tensor. Earlier we see that Son and his collaborators defined this only for even order tensors. So here in this paper, in these three papers, we found the definition for Moore-Penrose inverse of arbitrary order tensors. So after from these literatures, we are interested to work on reverse order laws for Moore-Penrose inverse of arbitrary tensor and what are its applications. And this is our object, that to demonstrate reverse order law of arbitrary tensor and find what are its applications. And my main result of the research work are this. We find that whenever the tensor A and B satisfies these two conditions, that A dagger A is observed by the tensor B star L B H star N A, its conjugate transpose A, observed by if A dagger star N A is observed by the tensor B star L conjugate transpose of B star N conjugate transpose of A, and A star N B star L B dagger star N A dagger is Hermitian. In that case, A and B satisfies reverse order law. Also, we find that if if A dagger A dagger star and B whole satisfies reverse order law, as well as A star and B Morpendus inverse equal to A Morpendus inverse star and A star and B whole Morpendus inverse star and A Morpendus inverse. In that case, also reverse order satisfies. These are the two results of my article. Whereas we also find more results. One can go through my paper to get another results. Also, we applied this reverse order law to find additive Morpendus inverse. That is, it is an important task to find what becomes Morpendus inverse of A plus B. And here we find that if the tensor A and B, if the tensor A and B satisfies I identity tensor plus A dagger star and B is invertible, and A star and A dagger is observed by B on pre-multiplication and on post-multiplication. In that case, A, B Morpendus inverse is exactly equal to identity tensor, inverse of identity tensor plus A Morpendus inverse star and B star and A Morpendus inverse. And here is another result. We are finding this inequality, that the B Morpendus difference of B Morpendus inverse A Morpendus inverse, where B is a tensor obtained by a small addition of small changes in elements of A, then this inequality satisfies. Here this norm is Frobenius norm, and 2 is second norm. And also we propose one sub-proper splittings, which may be helpful to find the solution of multilinear system using iteration process. And we defined it as A equal to U minus V, and satisfying the U and V, A satisfies by U star and U dagger star and A equal to A, and A is U dagger U is both observed by A on pre-multiplication as well as on post-multiplication. Then A equal to U minus B is called a sub-proper splitting, and we verified it that if A equal to U minus B is a sub-proper splitting, then we can express A equal to U star n I minus U dagger B. Also, if 1 is not an eigenvalue of U dagger B, in that case, A dagger, Morpendus inverse of A equal to I minus U dagger B inverse star n U dagger. And if the system Ax equal to B is consistent, then every solution of X satisfying U dagger Ux is equal to X also satisfies X is equal to U dagger B X plus U dagger B. And this is the content of this presentation is published in the article on reverse order law of tensors and its application to additive results on Morpendus inverse.
Thank you,
One
Bani.
this article to
In
find
fact, we're going to have some questions which I'm not in a position to take up right now because of time constraints.
Yeah, any questions?
Pradeep,
Or yeah, Manjunath,
we'll say
yeah.
thanks to speakers.
Yeah.
And
Okay.
move on to the next session.
Yeah, thank you very much for the nice presentation. Anyone new one is there, or is it over?
Yeah, Manjunath, all the best.
Yeah.
I'll ask you the question.
Okay.
Quickly.
Thank you very much, sir. Now we have another contributory talk. The speakers of these sessions are Chepuri Rajita, Kakatiya University, Warangal, India; Habibur Rahman, Pondicherry University, Puducherry, India; Harika Bolledla, TSWRD, CW, Warangal, Telangana, India; Himamshu Pokhriyal, Department of Data Science, PSPH, Mahi, Manipal. I now request Dr. Vasudeva Guddattu, Department of Data Science, Prasanna School of Public Health, Mahe, Manipal, to chair this contributory session. Over to you, sir.
Thank you for the introduction. So now I request Chepuri Rajita to present her presentation. And okay, so
the system won't work that fast.
hello. Hello.
Yes, sir. We are about to play. Yes, just a minute.
Yeah. Now I request Chepuri Rajita to present her paper.
I am thankful to the organizers for accepting my paper for the International Conference on ALAPS 2020 in the memory of Professor C.R. Rao on his centenary birth year, organized by Center for Advanced Research in Applied Mathematics and Statistics, Manipal Academy of Higher Education. I am C.H. Rajita, purchasing my PhD in the area of performance study and time-dependent queuing system with a server on vacation under the supervisor Dr. L.P. Rajkumar, Kakatiya University, Warangal. Here I am to present my research paper titled An Approach in Finding Optimum Solution for a Perturbation Fuzzy Transportation Problem with the permission of the chairs, and I presented my work. My title name is An Approach in Finding Optimum Solution for a Perturbation Fuzzy Transportation Problem. Contents: Introduction, definition, numerical example, perturbated optimum solutions, conclusion. Introduction. Makers play an important role and are responsible in taking strategic decisions in the expansion of an organization. Evaluation and alternative decision may sometimes turn to have a hug impact in the organization's failure. Fuzzy analysis is a study in which are related to uncertainty and vagueness and aiming at selecting the best alternative by using a step-by-step decision-making process can help to make more deliberations. In this study, we can consider a transportation problem wherein the cost, availability, and requirements are fuzzy numbers and they contributed with the alternative decisions. It is proposed to evaluate an optimum cost with an existing methods and find the shortcoming in decision making. Definitions: a fuzzy set of a basis set or reference set A is specified by its membership function mu, assigning to each x in a degree to which x belongs to a triangular fuzzy number. If A and B two triangular fuzzy numbers, then the arithmetic operations on A and B are addition and subtractions. Differentiation. Differentiation is the process of finding singleton value which represents the average value of triangular fuzzy numbers. Here, use the Agas ranking to diversify the triangular fuzzy numbers because of its simplicity and accuracy. Agas ranking technique. The Agas ranking technique, which satisfies compensation, linearity, additivity properties, and provides which results consisting of human intuition. F of R represents the set of all triangular fuzzy numbers. The robust ranking function f of R integral 0 to 1 0.5 a alpha power l a alpha power u into d alpha, where alpha is the alpha level cut of the fuzzy number. Trapezoidal fuzzy number. A trapezoidal fuzzy number f a of x, it can be represented by a membership function mu of x. robust ranking technique. If A bar is a fuzzy number, then the robust ranking technique is defined by R of A bar equal to integral 0 to 1, 0.5 into A alpha power L, A alpha power U, D alpha, where alpha is the alpha level cut of the fuzzy number. Numerical examples. In this paper, we can take a numerical example given by reference 11 and take the numerical example. A company has 4 sources and 4 the fuzzy transportation cost for unit quantity of the product from ith source to jth destination is Cij, where Cij is 3 by 4 matrix and fuzzy availability of product at source or and the fuzzy demand of the product at destinations respectively. Then the problem become as table 1 source and destinations. We are applying supply and demands. Now solve the solution. The fuzzy transportation problem can be formulated in the following mathematical programming form. The robust ranking techniques applying these table 1 and simplifying these values and trapezoidal these are trapezoidal fuzzy numbers and solving a singleton value and robust ranking technique is applying this value and after the integrations or robust ranking of 1 comma 2 comma 3 comma 4 equal to 2.5. Now similarly we can solve this all values, rank of all supply and rank of all demands after the ranking table 2. Now after applying Vogel's approximation method from the table 3 FD1, FD2, FD3, FD4 supply and demands. These are balanced transportation problem. The transportation cost is 123.5. Now using mode method, we optimum solution as given. The optimum solutions basic cells allocated in the cell and U1, U2, U3. Now the destinations V1, V2, V3, V4. The optimum solution is 122. Now with epsilon equal to 1.0, add basic cell, then calculate basic cell and non-basic cell. At least one non-basic cell is positive value, then the loop is involved in a basic cells. Now we assign plus theta, interchange the and theta values. We can solve this table. Then after the calculations, all delta ij is less than or equal to 0. The current solution is optimum. Therefore, the optimum solution is 1. Therefore, the optimum solution is 163. Now, with epsilon equal to minus 1.0, same as the sources and destinations, we can apply this some small epsilon minus 1.0. Now we add these basic cells and the after the calculations non-basic cells and the optimum solution is 18.4.25. Now with epsilon equal to 0.5, add the basic cells and after the calculations, the optimum solution is 125.5. With epsilon equal to minus 0.5, add the basic cells and the calculations of the transportation table. We can solve this optimum solution. These optimal solution is 100 and now add the epsilon equal to 0. From the optimum table. Now we can add the basic cells. Now consider these non-basic cells and add this. The loop is interchange the theta. U1 equal to 3, U2 equal to minus 9, U3 equal to 0 and V1, V2, V3, V4 values of the optimum solution is 119.7 with epsilon equal to minus 0.1. Sources and destinations are these loops is contained and assign the loop involving the basic cell. Now we assign the interchange the theta values. Now the optimum solution is 116.8. Conclusions. Studying fuzzy transportation problems is considered to be of great importance due to its close connection with human life. A linear programming problem of specific structure is a fuzzy transportation problem. If in a transportation problem all parameters and variables are fuzzy, we will have a fuzzy transportation problem with the values obtained by its weighted function of model. New cost coefficients are achieved and using Ogle's approximation method and Modi method, optimum solution is obtained. And later sensitivity analysis varying cost matrix, availabilities and requirements, optimum solution are studied. These are references. These are 9 references. Any
So thank you, Rajita, for the presentation. So quickly, can anyone have one question for the presenter? So if no question, I'll request second speaker, Dr. Habibur Rahman, to present his work.
Good morning, everyone. Today I am here to present my research work. The title of the presentation is Modeling of Computing Survival Data through Cumulative Incidence Function in the Presence of Middle Censoring. The outline of the presentation are on screen. The situation of computing arises when an individual can experience pre-mutually exposed type of event. For example, in liver transplantation, individual may receive the transplant and experience the death in waiting queue. The analysis of lifetime data in the presence of computing is based on two approaches. First is latent value time approach and second is cause-specific quantities. The following two cause-specific quantities gets considerable attention in lifetime modeling. First is cause-specific hazard function, which is nothing but the instantaneous failure to a particular cause in the presence of all other risk, which is given by equation 1. Cumulative incidence function is the cumulative probability of failure to a particular cause in the presence of all other risk, which is given by equation 2. Since the all events are mutually exclusive, therefore the overall hazard function and distribution function is given by HT and FT. To represent the heterogeneity in computing setting, the Cox proportional hazard model can be plugged through equation 3. Commonly used methods for analyzing the computing survival data based on cause-specific hazard function are non-parametric and semi-parametric. Advantage of non-parametric and semi-parametric inferences are they are easy to implement and free from the assumption of underlying distribution. However, parametric models are another available approach of modeling of cause-specific hazard function. If the parametric models select correctly, then they provide more robust and efficient estimate. Parameterization of cause-specific hazard function can be done by specifying some well-known distribution form for baseline hazard function in equation 3. When Choi and Gale estimate the absolute cause-specific risk by assuming that cause-specific hazard function follow piecewise exponential as well as exponential distribution. Bertrand and Dignam consider the constant cause-specific hazard function for the primary event of interest and other modes of hazard estimated non-parametrically. Jeong and Finn compared the viable cause-specific hazard likelihood estimation with direct likelihood approach by assuming improper complex distribution. Anjana and Sankaran assumed inverse viable reverse cause-specific hazard model under left censoring. Lee considered the parametric quantile inference for cause-specific hazard function with covariates. In this study, we consider the viable distribution as a baseline model through equation 4. Using equation 1 and 4, the CIF turned out in the following form given by equation 5, and it is observed that the expression in 5 is not in closed form. So to make it in closed form, we assume that all the shape parameters due to particular cause, different causes are equal. Therefore, the CIF have the following form given by equation 6. Censoring play a vital role in lifetime modeling. The computing analysis has been developed under various censoring schemes like right censoring, current status censoring, and interval censoring. In this study, we consider the middle censoring scheme, which was introduced by Jama Maladaka and Mangalam. distribution with parameter omega 2. Let lifetime TIs and censoring intervals are independent, then the observed lifetime TI is given by yi, which is TI when actual observation is observed, and random interval when censored observation is observed. Objective of the study: parametric formulation of cumulative incidence function using y-belt distribution in the presence of middle censoring. Obtain the point estimate by using maximum likelihood, midpoint approximation, and Bayesian methods. Obtain the interval estimates. The Bayes estimates are obtained based on informative and non-informative priors with two loss functions. Comparison of estimates based on simulation study and real-life data. Formulation likelihood function in the presence of middle censoring is given by equation 7, where delta j is the indicator function for the jth cause and theta is the all cause specific parameter set of all specific cause specific parameter. In this study, we assumed that n individuals where n1 and n2 uncensored and censored observation respectively. It is also noticed that sum of all delta ij equals to nqj corresponding to failure due to cause in uncensored and censored observation. The log likelihood function based on assumed model is given by equation 8. Midpoint approximation estimation. In MPA method, when the actual observation is marked by the random interval, then Ti is approximated by Ti star, that is the mean of the two endpoints, and the corresponding likelihood function is given by equation 9, and the log likelihood function based on MPA method is given by equation 10. From 8 and 10, it is observed that the estimates of the parameter cannot be obtained analytically. Therefore, we obtain the estimate using numerical technique. However, the normal equation under MPM method looks simpler than the MLE. Hence, the estimator of the parameter are turned out to be more easily. For obtaining the Bayes estimate MLE for CIF, we use the invariance property of the MLE. Bayes estimation. Bayes estimation. In the Bayes estimate, we assumed gamma prior for baseline parameter and normal non-informative standard normal non-informative prior for regression parameter, where Q1, R1, Q2J and R2J are the hyperparameters. We also consider the case of non-informative prior as a special case of equation 11 in a simulation study. The joint prior distribution of the non-parameters is given by equation 12. To obtain the joint posterior distribution, we use the Bayes theorem through equation 13, and it is observed that the expression of the joint posterior densities are not in the explicit form, so we use the MCMC method to generate the posterior sample. To obtain the Bayes estimate, we consider two types of loss function. First is asymmetric loss function, which is the squared error loss function and given by L1, and the Bayes estimate under squared error loss function are the posterior mean given by equation 14. Second is the asymmetric loss function, which is the Linux loss function given by L2, and the Bayes estimate under LLF are given by equation 15, where phi is the hyperparameter of the Linux loss function. When phi tends to 0, then the LLF is approximately equal to self. Otherwise, sign of the phi represents the degree of asymmetry. For interval estimation, we use asymptotic confidence interval, percentile bootstrap confidence interval, and Bayes credible interval. To observe the finite sample behavior of the proposed estimation, we consider a Monte Carlo simulation study. For simplicity, we consider two causes of failure and one single covariate X is generated from the standard normal distribution, and B assume three types of censoring proportion 10%, 20% and 31% by assuming different values for omega 1 and omega 2. In order to compute the hyperparameter, we use the likelihood estimate, and for non-informative prior, we assume the hyperparameter are close to 0, and for regression parameter, we assume normal non-informative prior. The hyperparameter of Linux loss function is fixed at plus minus 1.5. We consider for sample size 20, 50, 100 and 200. The whole process is repeated 500 times. The comparison of the estimates is made based on MSE, average length and coverage probability. These are the simulation results of my study. For fixed censoring proportion, as the sample size increases, MSE decreases. For MLE, MPA and Bayes estimate under both the brackets, which verify the consistency property of all the estimator. As expected for small sample size, Bayes estimates performs better as compared to MLE and MP estimate. It is observed that for fixed censoring proportion, average length for all the confidence interval are decreases as sample size increases, and most of the cases CP are very close to the nominal level. For fixed sample size, the average length of all the confidence interval is increases as censoring proportion increases except for some values. Moreover, we observed that the credible interval based on informative prior are better than among the interval estimate in terms of average length and coverage probability. Real life application. We analyzed liver transplant data from between 1974 to 1984. In this 10-year study period, a total of 424 patients are enrolled in the study, in which 312 patients were randomized to receive depenicillin and placebo treatment. In the end of the study, 161 patients died, another 25 patients were received the liver transplant, and 232 patients were lost to follow-up. For the analysis purpose, one single coverage treatment is considered, which verifies the proportionality of the hazard in figure 2. For checking the goodness of it, we use the Kolmogorov distance formula for fitted model and empirical, which is the distance is 0.0331 and the corresponding p-value is 0.737, and which indicates that the model cannot be rejected for this data set. Figure 1 shows the graphical fitting of the viable distribution for this data set, and figure 2 is the Anderson plot for checking the proportionality assumption of the treatment for both the transplant and death. Next, we have created an artificial dataset by material censoring, whose left end points as the observed time itself. The width of interval is generated from exponential distribution with mean 10. Then all the censored individuals are considered as the middle censored observation. The computing outcome variable for middle censored observation are randomly assigned from the death and transplant. We applied the proposed method of estimation to obtain the point and interval estimates of the known parameters and CIF. The result of point and interval estimates of unknown parameters are presented in table 1, and the result of CIF for is given by figure 1 for transplant and death. Conclusion. In this study, we consider the modeling of cumulative incidence function using viable cause-specific proportional hazard model in the presence of middle censoring scheme. Both classical and Bayesian approach are utilized for obtaining the estimates of the known parameter and CIF. The simulation study shows that the Bayes estimates based on informative prior perform well as compared to other estimates in terms of MSE and average length and coverage probability. All the estimator verified the consistency property in simulation study. For compared dataset goodness of fit criteria provided the viable model good fit to the data. Coverage treatment hazard assumption of the model. These are some references. Thanking you.
Thank you, Dr. Rahman, for the presentation. Quickly, can we have one question? Yeah. So if no questions, then I request next speaker, Ms. Harika Balleda, for her presentation. I think audio is muted. ಹಲೋ, ಆಡಿಯೋ ಬರ್ತಾ ಇಲ್ಲ ನಯನ್.
Yes, sir. We are trying to do it.
Okay. Sorry, there was a technical error. They are trying to sort it out.
Vasudev,
Sir.
can you hear me?
Yes, sir.
What we do is entire next session shared by Srimati Maya will be adjourned to tomorrow. Now this will complete it properly. Okay, after correcting this error.
Yes, sir. Yes, sir. Yes, sir.
Okay.
Yeah, thank you, sir. Yeah.
Vasudev, can you hear me?
Yeah, yes, sir. Yes, sir. I can hear you, sir.
Okay, my speaker was mute. Okay, we'll sort it out and we'll complete the session in this particular day itself right now. Okay.
Yes.
We'll make appropriate announcement on rescheduling the next 1 hour session, whichever is has been chaired by Professor Maya.
Dr. Maya.
Good morning. Myself, B. Harika. I am doing
Dear all, there was some technical glitches. So we are replaying the current presentation once again, with the permission of the chairperson. Sir, Vasudev sir, can we do the?
Yes. Yeah, we can continue. Yes.
Yes, sir. Thank you. The presentation is continuing.
research under the supervision of Dr. L.P. Rajkumar sir. Today I am going to give a talk on generalized triangular and symmetric splitting method for steady-state probability vector of stochastic matrices. Contents: Introduction, fundamentals of stochastic matrices, generalized triangular symmetric splitting method for steady-state probability vector of stochastic matrices, and finally references. Motivation. Nowadays, internet traffic is rusty in behavior. One of the major challenges for traffic engineers is internet traffic. Based on the performance measures, one can conclude the quality of services and stability criteria. Research philosophy. The switch or router is modeled as queuing system, and we can find out the steady-state probability vector by using the matrix geometry techniques. And after finding the steady-state probability vector, we can find out the performance measures, and based on the performance measures, we will conclude the quality of services. And after finding the quality of services, one can dimension the switch or router. Fundamentals of stochastic matrices. Markov modulated Poisson process has been used for modeling of aggregate voice sources and video sources. This model is a doubly stochastic Poisson process where the rate process is determined by the state of a continuous time Markov chain. The Markov modulated Poisson process is characterized by infinitesimal generator Q of the underlying Markov process and the vector lambda of the arrival state. The matrices Q and big lambda are given as follows. The mean arrival later lambda of Markov modulated Poisson process is given by lambda equals to pi big lambda E, where pi is the steady state probability vector of Q. The steady state probability vector pi of Q satisfies the equations pi into Q equals to 0 and pi E equals to 1. This diagram represents the transition diagram of an end state Markov modulated Poisson process. Coming to our problem, the generalized triangular and symmetric splitting method for steady-state probability vector of stochastic matrices. In most of the cases, when the network nodes are modeled as queuing systems, the problem of computation of performance measures is reduced to that of steady-state probability distribution vector of transition rate matrix or transition probability matrix. Therefore, it is of key importance to investigate the pertinent linear systems. The significant improvements in convergence rates can be achieved from the Krylov subspace methods, two-splitting and multi-splitting iterative methods. The alternative methods, namely Hermitian and skew Hermitian and positive definite skew symmetric methods, which converge unconditionally to the unique solution of the system of equations. Moreover, the triangular and symmetric iteration method has been developed and discussed for solving the positive definite linear system of stochastic matrices. Here, P is the stochastic probability matrix. If sum of each row in P and sum of each column in P is 1, then this matrix is also called as doubly stochastic matrix. The steady state probability, the steady state distribution vector pi satisfies the equation pi into P equals to pi. That implies pi q equals to 0, where q is the matrix. In this matrix, if each row sum and each column sum is 0, then Q is doubly stochastic rate matrix. Some of the definition related to our talk. Any matrix A belongs to R power n cross n of the form A equals to Si minus B, S greater than 0, B greater than or equals to 0 is called an M matrix if S is greater than or equals to spectral radius of B. If S greater than spectral radius of B, then A is non-singular M matrix, otherwise A is singular M matrix. A non-symmetric matrix A belongs to R power n cross n is M matrix if its symmetric part A plus A transpose by 2 is M matrix. A non-symmetric matrix A belongs to R power n cross n is positive definite if its symmetric part is positive definite. The coefficient Q of the equation 3.2 has one-dimensional null space. Thus, triangular symmetric iteration method cannot be directly applied to solve the linear system. So, we go for a regularized linear system which is in the form of A bar x equals to 0, where A bar is Q transpose and x is pi transpose. Then there exists a non-negative constant epsilon greater than 0 such that the above equation can be converted to the preconditioned linear system Ax equals to En, where En is the unit vector. Lemma. A stochastic rate matrix Q belongs to R power n cross n is a matrix. For any non-symmetric stochastic rate matrix Q belongs to R power n cross n where there exists a constant epsilon greater than 0 such that A equals to Q transpose plus epsilon In is positive definite if all its real eigenvalues are non-negative. This theorem is very useful in finding the convergence criteria of the triangular symmetric iteration method. Consider the coefficient matrix A equals to D plus L plus U. This is the schema which we were used to solve the problem, where D is the diagonal matrix with the diagonal entries and L is lower triangular matrix and U is the upper triangular matrix, where D is defined like this and L is defined like this and U is the defined like this. The triangular and symmetric splitting method is generalized on the regularized stochastic matrix as follows. That means A is splitting as triangular and sum of triangular and symmetric matrices. That means we can also written as A equals to T plus S, where T is the triangular matrix with the non-negative diagonal elements and S is the positive symmetric matrix with the positive diagonal elements and negative off diagonal elements. To find the solution of the regularized linear system, we can use the iterative method described. We will guess the initial value x0 and we will calculate the next approximations by the following scheme. We will continue this process until x power k converges to for any positive constant alpha. The above iterative scheme can also be written as in this format. This is the iteration matrix of the triangular symmetric iteration method. M of alpha is the iteration matrix of the triangular symmetric iteration method and N alpha equals to like this. If the spectral radius of M of alpha is less than 1, then the iteration method is convergent. We assume the lemmas 3.3 and 3.4 from the paper. This paper is a reference list. Let W of alpha equals to alpha I minus T into alpha I plus T whole transpose, whole inverse. If T belongs to R power n cross n is a positive definite matrix, then we have two norm of W of alpha less than 1 for our alpha greater than 0. If the matrix S is the symmetric part of the coefficient matrix A of the regularized linear system 4, then there exists epsilon greater than 0 such that the matrix S is positive definite. We prove the following lemma 3.5. Let H of alpha equals to alpha I minus S into alpha I plus whole inverse If S belongs to R power n cross n is a positive definite matrix, then we have 2 norm of H of alpha is less than 1 for all alpha greater than 0. 3.3 and 3.4 are previously proved in some other paper. Here we will prove lemma 3.5. The numerical results also not discussed here, but we will find out the numerical solution for steady state vector using the triangular symmetric method, and after calculating that we will compare with the other existing methods. Therefore, the convergence rate of triangular symmetric method is very fast when compared to other previous existing iterative methods. Finally, my conclusion is, in this problem, we present generalized triangular symmetric splitting iterative method for the regularized matrix of the system of stochastic matrix. We proved that the regularized matrix is positive definite under specific condition. We conclude that this method unconditionally converges to a unique solution, and the convergence rate is rapid when compared to other existing methods. And these are my references. Any queries or suggestions? Thank you.
So thank you, Harika, for the presentation. So can we have quickly one question for the speaker? So if no questions, then I'll invite next speaker, Dr. Himanshu Pokhriyal, for presenting his presentation.
Good morning, everyone. My name is Himanshu Pokhriyal. I am Assistant Professor in Department of Data Science, Prasanna School of Public Health, Manipal Academy of Higher Education, Manipal. Today, I'm going to present my work on testing for measurement error in regression with autoregressive innovations. This is a joint work with Professor N. Balakrishna from Cochin University of Science and Technology. This is the outline of my presentation. We will start with the introduction to the problem setup. Then we see how the test was obtained, which is followed by some simulation study and conclusions. So first of all, let's consider the multiple linear regression model with k independent variables given by equation number 1. The error sequence ET is assumed to follow a stationary autoregressive process of order P given as ARP and given in equation number 2, such that the roots of the polynomial phi b lie outside the unit circle, and the sequence AT is IID with mean 0 and variance sigma square A. We analyze the regression models given in equation number 1 and 2 when there are measurement errors in the response as well as in the regressor variables. So suppose that we observe the surrogate instead of the true variable or the true regressor variable xjt. So we are observing wjt instead of the regressor xjt, and we are observing surrogate rt instead of the true response variable yt for all j equals to 1 to k and t equals to 1 to n. So assuming the additive structure, we can write the forms of these wjt and rt as equation number 3 for all j equals to 1 to k and t equals to 1 to n. So here the sequence uj, t and the sequence vt are the measurement errors such that ujt's are IID with mean 0 and variance rho j sigma square a, and vt's are IID with mean 0 and variance rho naught sigma square a. So note that rho naught and rho j's for all j are strictly greater than 0. When they are equals to 0, that means the model has no measurement error in the scenario, and then further for all UJTs and VTs are independent of XT, ET and AT sequence. So in this paper we consider the testing problem. We test the null hypothesis rho naught equals to rho 1 equals to and so on till rho k equals to 0 against the alternative rho j greater than 0 for at least one j equals to 0, 1, so on till k. So if you see here, under h0, there exists no measurement error, either in response or regressor variable, whereas h1 indicates the presence of measurement error. Now using equation number 3, the model given in equation number 1 becomes equation number 4, and Bt is given in equation number 5, also known as the composite disturbance term. And if you see carefully, this Bt is the sum of an ARP process Et and the linear combination of white noise given in equation number 6. Granger and Morris and Hamilton have already shown that the sum of an ARP process and a linear combination of white noise error series results in an ARMA PV process. Using the same result, equation number 5 can be written as equation number 7. So if you see, Bt here is now an ARMA PP process given as phi b Bt equals to theta b epsilon t. Phi b and theta b are both pth order polynomials given as such, where epsilon t is a sequence of IID random variables with mean 0 and variance sigma square epsilon. Here the parameters theta1, theta2, theta3 and so on till theta p and sigma square epsilon can be determined by solving for the variance equations of both sides in equation number 7. So we have equation number 7 and we solve for the variance of this equation, and then we get equation number 8. And then comparing the coefficients of the Bakchelov operator B on both sides, we can get the estimates of, or we can determine the parameters theta1, theta2 till theta p and sigma square epsilon. So in order to proceed with the estimation and then the testing of hypothesis problem, we make the following assumptions. The first assumption is about the stationarity and invertibility of the ARMA PP process, and the roots of polynomial phi b and theta b should lie outside the unit circle and they should not have any common roots. The sequence AT are assumed to be normally distributed with mean 0 and variance sigma square a. The sequence UJT are assumed to be normally distributed with mean 0 and variance rho j sigma square a. The sequence VT are assumed to be normally distributed with mean 0 and variance rho naught sigma square a. UJT for all j and VTs are independent of each other and are also independent of AT for all t. So from assumptions 2 to 5, it follows that epsilon t is a sequence of IID normal random variables with mean 0 and variance sigma square epsilon. So finally, we can write our model as equation number 9. If you see, equation number 9 is now in terms of the surrogates instead of the true values, which can further be written as ARMA PP representation given in equation number 10. So the log likelihood of the parameter theta for the model 10 is given in equation number 11, and the partial differentiation of this log likelihood value with respect to the rho j's under h0 can be computed as summation I equals to 1 to p. So if we first differentiate the log likelihood with respect to theta i's, and then we multiply it with the differentiation of theta ith with respect to the rho j's under h0. It's given in equation number 12. So hence under h0, del L by del rho naught under h0 is given in equation number 13, and for all j equals to 1 to k, del L by del rho j under h0 is given in equation number 14. So the LM test statistics takes the form under h0 as equation number 17. So we have the test statistics T0. So under h0, T0 converges in distribution to standard normal variable as n tends to infinity, and it rejects h0 for large values of T0 at alpha level of significance. Note that the LM test statistics obtained in equation number 17 is free of the estimates of regression coefficients of the original model. It depends on the autoregressive parameters of the error sequence given in equation number 2 and the variance of the measurement errors in both response as well as regressor variables. Now we come on to the simulation study. We investigate the performance of the test by simulations for various parameterizations of the model. For illustration purposes, we consider a simple linear regression, y2 equals to 1.5 xt plus et, where the innovation sequence takes one of the following forms. Model 1 is a AR1 representation where the AR coefficient can take any one of the three values 0.9, 0.5 and 0.1. Model 2 is an AR2 representation where the combination of phi1 and phi2 can take any one of these three forms, and AT is taken to be a standard normal random variable. Now, if you see, the AR coefficients are taken as such that the AR process is stationary in both model 1 as well as model 2. So here the regressor xt is fixed and generated from a normal distribution with mean 550 and variance 0.5. For every combination of models, we study the power performance of the proposed test for sample sizes 50, 100, 250 and 500. We repeated the simulations 5,000 times for different sample sizes. All the computations were carried out in RStudio Cloud platform. Now table 1 presents the power performance of model 1 for different values of autoregressive parameters phi1. It is seen that as rho 1 increases, the power increases for fixed sample size n. For higher values of phi1, the power performance of the test is much better than when phi1 takes smaller values. So when phi1 equals to 0.9 or 0.5, the power increases as n takes larger values, although the power decreases when phi1 is equals to 0.1. Similarly, for model 2, table 3 represents the power performance of the LM test. Here again, as rho 1 increases, the number of rejection increases for fixed n. For fixed rho 1 and varying n, the power increases as n takes the larger values. Table 2 and table 4 represent the power performance when the measurement error is present in both response and regressor in model 1 and 2 respectively. As rho 0 and rho 1 increase, the proportion of rejections increases. The power performance of the test was reasonably good and promising in detecting any presence of measurement errors. So these are the conclusions. These are some of the references. Thank you. Thank you for listening.
Sir, Vasu sir. Sir, because of the technical issues, the next session has been postponed to tomorrow. We will be announcing the time in no time. One contributory talk from the next session would be happened now. Will be played right now. That is a contributory talk by Dario Ferraria from University of Beira Interior, Portugal. I request Dario Ferraria to switch on the video and ready for question and session. Now we'd like to play the video. We request Vasudev sir for permission.
Yeah, you can continue. Yeah.
Thank you, sir.
It's okay. It's okay. Thank you. Hello, my name is Dario Ferreira, and the title of my presentation is Sums of Squares in Prime Factorial Designs. This is a joint work with Professors Sandra Ferreira, Célia Nunes, and João Tiago Mexia. We are all from Portugal. This is the outline. So, prime factorial designs are P up to n designs where P is a prime or a power of a prime. This kind of models are very common in industrial experimentation. The most of such experiments use two-level factors, but experiments with a larger number of factors are also quite common. The advantage is that these models allow the simultaneous study of a larger number of interactions compared to classical approaches. A disadvantage is that the procedures for obtaining the sums of squares can be a bit cumbersome. So, the goal of this presentation is to present a recurrence way for obtaining the sums of squares in order to alleviate these difficulties. The method may be applied to cases with any number of factors and levels, even when it's neither a prime or a power of a prime. We illustrate the method with an example. So, in what follows, we will use mode R arithmetic, where the numbers wrap around when reaching R, and we denote A plus B in mode R arithmetic by this way. So, consider a model with U factors, P prime levels, then we will have P up to U treatments. With XH, the level of the H factor, the treatments may be represented as we have here. So we have the linear function represented in 1. Note that there are P up to U of these functions, of which QU are reduced. We say that a function is reduced if the first non-null coefficient is 1. Let Li be a reduced linear function, Ai be the vector of coefficients of the ith reduced linear function, and Jx be the index of treatments x. The functions in Li are ordered, coming first x1, then x2, then x1 plus x2, and so on until we have this. These functions constitute the LIP square functions. Going forward, we will have LP plus 1x, which is x3, and then the other functions of LIP up to 3. The indexes of these functions are obtained by adding this to the index of this function. We'll now consider recurrence relations. So we'll associate PU with a KU times PU matrix whose row vectors are associated with the functions of LIPU. Let's say that it's BU. So B1 will be this function. BU plus 1 may be written as we have here, where all the sub-matrices are KU times PU, except this second, which will have one single row. It may be seen that the first matrices in the first row will be equal to BU, and that the one in the second row, which will be that matrix with only a single row, will be equal to this product. So we may write BU as we have here. Now let's define delta B VR, which will be a vector with all components null except the ones with value V in the rth row of a certain matrix B, which will be 1. So to exemplify, let's consider matrix B as we have here, and so delta B01 will be 1, 0, 0. Why? Because we have to look for 0 in the first row, whereas 0 is here, so we'll have here 1, and the remaining positions will be 0. In the same way, we'll have delta B12 is 0, 0, 1, because we'll have to look for the 1 in the second row. So whereas the 1 is here, so we have here 1, and the remaining positions are 0. Now we can associate this kind of matrices to the functions. So we'll have these matrices. It may also be shown that the sum of squares associated to that functions are given by this product, where AI is this product and CP is obtained by deleting the first row of a J times P orthogonal matrix. We have an example where we consider a T up to 3 model. The data is presented here in this table. So in this case, we'll have 13 reduced linear functions. Matrices BU will be, well, for B1 we'll have 0, 1, 2, and then for B2 we will have here 0, 1, 2, it's B1, B1, B1. This the row or the matrices with a single row, and here this matrix is obtained by summing. For example, here we have 1 plus 1 is 2, and 2 plus 1 is 0 in mode 3, of course. Finally, B3 is represented here. So here, this is B2, B2, B2. This is that matrix with a single row, 0, 1, 2. And here, for example, we have 1 because we are summing 1 plus 0 is 1. Or here we sum 1 plus 1 is 2, and so on. So from 12, one may obtain, for example, that delta B matrices. For example, here for the first row, for Bx1, we'll look here in the first row of this matrix. So for the first row here, we look for 0. Then here we look for 1, and here we look for 2. So where's the 0? It's in this position, in this. The 1 is in the second position. The 2 is in the third position. So here we have 1, 0, 0, 1, 0, 1, 0, 0, 1, and 0, 0, 1, and so on. Now, if we consider these matrices, we may write the matrices B as we have here. Now, considering this orthogonal matrix, we obtain C3 by deleting this first row. And then, using 13, we may obtain the sum of squares. So here we have the table with the decisions, with the 13 linear functions. X1 is for factor 1, X3 for factor 3, and here we have interaction between factor 1 and factor 3, and here another part of the interaction of factor 1 and factor 3. So we do not reject, we reject. If we want to obtain the sum of squares obtained by the ANOVA, by the usual techniques, we just have to consider, well, for the single factors, they are the same. If we have the interactions, we just have to sum, for example, interaction between factor 1 and factor 3. We sum these two. Here it is. And here we have the table using ANOVA just to confirm that the sum of squares may be obtained this way. So note that if we use ANOVA, we reject the null hypothesis for interaction 1, 3 between factor 1 and factor 3. Here we reject, but using the prime basis factorial method, the null hypothesis corresponding to function x1 plus 2x3 is rejected, as we saw, but the null hypothesis corresponding to function x1 plus x3 is not rejected. So, as final comments, I can say that prime factorial designs allow the simultaneous study of a larger number of interactions compared to ANOVA, but if wanted, the classical sum of squares can be easily obtained. The procedures for obtaining the sum of squares can be a bit cumbersome, and we presented a recurrence way for obtaining the sum of squares for cases with any number of factors and levels in order to lighten the calculations. So here are some references, and thank you very much.
Vasudev.
Yeah, I'm audible, sir?
Yes, sir.
Yeah. So I'll thank all the speakers of the session, and I'll thank all the organizers for giving me opportunity for chairing the session. So over to you, sir. Yeah.